Hi everyone! In this lecture, I will show you an iterative method to solve a given system of linear equations, namely Jacobi method. And let's first start with a simple definition or our main goal for using Jacobi method, and then I will start explaining the details related to Jacobi method. Well, first of all, Jacobi method is an iterative algorithm, as I said earlier, for solving a system of linear equations where our coefficient matrix is a square, strictly diagonally dominant matrix. Well, in this definition, there are two hidden facts that we need to point out clearly. So one is the fact that it should be a square matrix, and one is that there's the definition like strictly diagonally dominant matrix. So what are these? And why they are important for us? So let's first answer these questions. Okay, but first of all, we should understand that Jacobi method is an approximation technique. So if we use Gaussian elimination method or Gauss-Jordan method, we were able to find the exact solutions. But in iterative algorithms, we try to find the best solution possible. In other words, by saying best solution, I mean the solution within the predefined or pre-assumed error tolerance. So how can we do that, and how is that possible? Let's now see that. But before even that, before diving into the details of Jacobi method and how we can apply it, we first understand what a square strictly diagonally dominant matrix is and why this should be satisfied. So we know that if our matrix has equal number of rows and columns, then it is called a square matrix. What I mean by that? So if we have an n by n matrix where n is the number of rows and the second n, well, the first n is of course the number of rows and the second n is the number of columns, then we say that we have a square matrix. But in our case, when we represent a system of linear equations in the matrix form, what this means? Our rows actually corresponds, right, each row actually corresponds to one equation in the system from top to bottom, right? And each column actually represents the number of unknown variables. So it means that if we have an n by n matrix which represents our system, then that means we have n equations and n unknown variables. This is important for our method, for our Jacobi method. Why? Because in Jacobi method, actually, we try to converge to a solution, to the exact solution that we have not known earlier, okay? That we have not known previously. We just start with an initial guess and try to converge that solution or try to find that solution by iterating through the updated values of the unknown variables. And to do so, actually, we should be ensured that our system has the unique solution case. What I mean by that? We have three different possibilities. We can have unique solution, we can have infinite number of solution, and we can have no solution at all for a system of linear equations. But if we don't have a square matrix, that means suppose if we have an m by m matrix, then that means we have n equations and m unknown variables, and that means it is possible to have an infinite number of solutions or an empty solution. So we might not have a solution at all. This is something that we don't want to run into. Why? Because we try to, suppose we have no solution, but we try to converge to a solution which is not there at all. So it is just like chasing our tail. We don't want our system to have no solution case. And infinite number of solutions doesn't work for Jacobi method as well. Why is that? Because suppose we have many infinite many solutions, but we actually try to converge one exact solution. So how could that happen? So unless we have only one single point that is the solution set, we will not be able to converge to that exact value at all if we have infinite number of solutions, and some values will be diverging whereas some values will be converging, but we will never be able to reach to the exact solution in the case of infinite solutions either. So we need to have the unique solution case to apply this Jacobi method. All right, and this is one of the reason here to be square matrix, but it is not enough either. Even in the square matrix case, we can have again different possibilities for the solutions, so we don't need to have that unique solution case. So somehow we need to add an additional property that would really guarantee us to converge to the real value. So, and the second additional condition is that the strictly diagonally dominant matrix condition. So it is not enough to only have a square matrix, but it also needs to be strictly diagonally dominant. And what I mean by that, let's point that out. Let's explain or define what a strictly diagonally dominant matrix is. And here's the definition. Well, if I want to technically define what a strictly diagonally matrix is, I should write it actually in this manner. So the absolute value of the AII entries in the matrix, which is actually, these AII entries actually are the main diagonal entries. Since we have a square matrix, we have the main diagonal, right? We know that. But I will show it in a minute or so. And this absolute value should be strictly greater. By the way, I say strictly, right? And what I mean, we don't insert equality, so there is no equality. And if we erase equality, that means strictly greater. But if we add also equality condition here, that means greater or equal than something else on the right hand side. Okay, but this is the strictly greater, so we should be careful about it. But greater than what? Greater than, well, let me again write it in red colors, so just to bring your attention to this point where I is not equal to j, we sum over the absolute values of aij's. And what I mean by that, so what does that mean? So this is the technical definition, but what I mean by that, let's get into that. All right, so let's get into details. Here's the thing. What I mean is this. Suppose we have a square matrix. Well, first of all, we need to have a square matrix, right? Otherwise, we can't talk about the main diagonal entries. And suppose this is the values given. All right, so 10, 2, 3, say it, okay? And say -2, say 8, and say 4, 1, 5, and 50. Now let's see, is this matrix is a strictly diagonally matrix? Is it really strictly diagonally dominant matrix? Let me put it that way clearly. Okay, so what am I gonna do? This formula says that suppose we take the value a, suppose we take the value I is equal to 1. Okay, so when I take the value I is equal to 1, that means over the summation I is a constant value. I look at the first row, so this value 10 should be greater than, strictly greater than the sum of the other values in the same row, which are 2 and 3. And what I mean is, I check to see whether or not in the first row 10 is greater than 2 plus 3. And I also take the absolute values of this, but since there is no negative value in the first row, I don't need to do that, right? So, but you know, there is the absolute value here, so don't forget about that. So this is actually the absolute values, sum of absolute values. Well, actually, let me write it even more clearly. Actually, this is the correct way, right, to say it. Okay. So this is equal to 5, and 10 is greater than 5, then the first row satisfies the condition to be a strictly diagonally dominant matrix. How about the second row? So I examine row by row to see each row satisfies this strictly diagonally dominant condition. And for the second row, I look at the second main diagonal element. By the way, you know, the main diagonal elements are those that are on this line I just draw. See? 10, 8, and 15. If I draw the main diagonal, and the main diagonal entries are those of values that are placed on that line. So 10, 8, and 15 are the main diagonal entries for this matrix. So we have a 3 by 3 matrix here. So it's a square matrix, and this is the main diagonal entries. So they should be strictly greater than the sum of the other values in the same row. So for the second row, I check the same property. Let's see whether or not it's satisfied. So what should be? Now the value of I is equal to 2. So 8, I check to see if 8 is greater than, in the second row, besides the value 8, we have -2 and we have 4. So absolute value of -2 plus absolute value of 4. So this is 2 and this is 4 and the sum is 6. And this is 8. So 8 is greater than 6, right? Strictly greater than 6. So the second row satisfies the strictly diagonal dominant condition as well. How about the third one? How about the third row? And the main diagonal entry in the third row is 15. And the absolute value of 15 is what? Is greater than absolute value of 1 plus absolute value of 5. Why do I sum this 1 and 5? Because in the third row, besides 15, we have 1 and 5, right? So I need to sum them up. And of course, I need to sum their absolute values, because this is the definition of strictly diagonally dominant matrix. And again, 15 is greater than 6, right? Strictly greater than 6. And the third row also satisfies this condition. And what I can say is that, right, this is a square matrix, and this matrix satisfies the strictly diagonally dominant matrix conditions. So we have a square strictly diagonally dominant matrix, right? And why these two conditions are important? Well, because this is an iterative algorithm, and we try to converge to an exact solution by starting at some initial guess. So in order to ensure that we will converge to exact value, we need to check to see whether or not these two properties are satisfied. And if this property is satisfied, in other words, if we have a square strictly diagonally dominant matrix that corresponds to our system, then we guarantee the convergence. Alright, that's a very important point. And again, Jacobi method is an iterative algorithm. So we iterate through the values of the unknown variables, and we update their values in each iteration. And to converge, to really converge to a certain point, which is the actually point we're looking for, which is the actually our solution set, in other words, then we need to ensure that these two properties are held. All right, this is just the definition, and this is just the preconditions that we need to check. How about this algorithm? So how this Jacobi method works? Now let's dive into that. Here's the basic steps that we should follow to apply Jacobi method in order to find the solution to our system. And The very first step, guys, here is that the very first step, I just circled in red, write each equation solving for its own variable. And what I mean by that, let's get into that point. We need to write each equation. In other words, actually, we rewrite each equation with respect to one of the unknown variables and move the other unknown variables along with their coefficients to the right hand side. In other words, we isolate each unknown variable in equation from top to bottom. And how can we do that? Let's give an example. So suppose here's the first equation. Suppose we are given, in our system, we are given this equation. This is the very first equation. 5x plus 2y minus z is equal to, say, 9. Okay, say 9. So what am I gonna do? I will isolate, if it is the first equation, guys, okay, what is my first unknown variable? My first unknown variable is x. And from top to bottom, from the very first equation on the top, I will go to the very last equation at the bottom and isolate each unknown variable, each corresponding unknown variable in each equation. So how can I do that? So besides the first unknown variable, I move all the other values on the left hand side to the right hand side. I just move them to the right hand side. So what I have now? So what I have is x is equal to, and then dividing by the coefficient of x, 1 over 5 in square brackets 9 minus 2y plus z. In other words, I rewrite the first equation with respect to the unknown variable x. In other words, with respect to the first unknown variable. So the first equation is rewritten with respect to the first unknown variable. And if we, in the second equation, then this time I will write the second unknown variable. In other words, I isolate the second unknown variable. And then in the third one, I isolate the third unknown variable. And in the nth equation, which is at the bottom, then I isolate the nth unknown variable. So it is just like a process of rewriting each equation in a manner that would enable us actually to start the iteration process. And you will understand what I mean by starting the iteration process in a few minutes. All right then. Now this is what it means, writing each equation solving for its own variable. So actually we isolate each unknown variable, each corresponding unknown variable in each equation. And we do the same process for all of the equations. Alright, if I want to formulate this process, what does it mean? If you notice, if I want to formulate this, you see that, well, I move everything besides the unknown variable that is of our concern to the right hand side of the equality, and actually I subtract them from the right hand side value and then divide it by the coefficient of the corresponding unknown variable. If I formulate this and, for instance, say I want to do it for the unknown variable xi, right? Xi is nothing but it could be x1, x2, xn. How many unknown variables we have? We don't know, but one of them. Okay. If I want to formulate this, so this is something like, it's like dividing by diagonal entry of that corresponding unknown variable, and in the parentheses we subtract bi, and bi represents the right hand side value. In this case, this 9 value, the value 9 represents bi, minus everything on the left hand side besides the corresponding unknown variable, right? Besides x. So 2y minus z, we just move them to the right hand side of the equality. And if I want to formulate it, it is something like, we can represent it by a summation sign. We move everything to the right hand side, besides itself, right? So I can write it aij times xj, and xj represents the other unknown variables which move to the right, and aij's are their coefficients. So in this case 2y and minus z actually corresponds to this summation, and 9 corresponds to bi, and aii corresponds to 5 in our example. And we do the same for each equation, right? If we take the value I is equal to 2, then we do the same thing for the second equation. And if we take the value I is equal to n, we do the same thing for the nth equation. All right. This is the first step. So we need to write each equation in terms of the isolated unknown variable. And in the second step, okay, suppose we write each equation, but here we will not apply a method like Gaussian elimination or Gauss-Jordan that we have learned so far. We here use a very different technique, an approximation technique, an iterative procedure to compute the newly explored values. And here actually we don't know anything but the values of each unknown variable in terms of the other unknown variables, right? So in other words, we just rewrite them based on the right hand side value and the other unknown variables and along with their coefficients. And to start the iteration, all right, so if I want to find the values of these unknown variables in the first iteration, I need a start point. So I need to take an initial guess. This is called an initial guess. And by initial guess, what I mean is the very first guess of the variables of the unknown variable, actually for the values of the unknown variables. So, but there is one problem here. If we are not given an initial guess, then what are we going to do? If we are given an initial guess, that's simple. Just plug the values in our first iteration and then keep computing the values, newly explored values, newly obtained values. But if we are not given an initial guess, the simple thing we do is we just take the initial value of each unknown variables, or for each unknown variables equal to 0. Suppose we have 3 unknown variables and we are not given an initial guess, then what we do is we just simply take the values of each unknown variable equal to 0 and use this vector or these values as our initial guess. So this is the actually step that we should take, the second step we should take. So choose an initial guess. Okay. And if you are not given an initial guess, just give all the unknown variables zeros. So just construct the vector of zeros for the initial guess. And in the third step, after giving the very first initial guess, we start iterating. So we find the new values with respect to the older values. So by saying older values, the values that we obtained in the previous iteration. And when we find the new values, at the next iteration, we use our new values. And then for the fourth step, this is actually one of the most important steps. Okay, now at any iteration in this computational procedure, you know, we reach to some newly obtained values, but there's an important point that we have not mentioned about yet. All right, this is an iterative algorithm, right? We define an algorithm, in other words, a set of rules or a sequence of instructions that we should follow in order to produce the desired output. In our case, for the Jacobi method, our desired output is the solution for our system. But The question is, when should we stop? In other words, we need to decide a termination criteria so as to stop our algorithm and produce some output, right? Otherwise, this computational task will go forever. So we will get into a loop, what is known as, from the computer engineering point of view, right? We continue to compute forever because we don't have any termination criteria. Unless we have a termination criteria, it will just competing and competing, right? We don't even understand whether or not we get closer to the solution because we need some stop criterion. And how would we decide that? Well, there are some alternatives to stop this computational procedure, and one of them is very simple. We just put an upper bound on the maximum number of iterations that we will make. So suppose I predetermined a value of 100 for the maximum number of iterations. So I just iterate 100 times and then stop and then produce the output that I've just found at that moment. That's one way. So it's simple as that. Another way is that maybe it would be more plausible, and this is putting in what is known as an error tolerance or error rate. So what I mean by that, so in other words, error tolerance means how much error we can tolerate. In other words, what is the accuracy rate we desire to reach in the end. So we can look at the situation from this point. In other words, well, beforehand, what is an error rate? What does it mean by an error rate? An error rate, if you want to, for instance, if we have a computational procedure, suppose in our case, we don't know what it is, but we know that our system has some exact solution, right? And this computational algorithm, this iterative algorithm, also tries to calculate that value. Okay, but there would be some error because we are using an iterative algorithm where we try to just converge to the exact solution, which we don't know what it is. So here's the thing for the fourth step. The difference between the actual value or the original value and the value that just we computed, say xo, which is the original value, and xc, this is the computed value, and the difference, the absolute value between this difference is the error we reached, right? We have some sort of error. So there is the actual value and there is the computed value, and the difference between the actual value and our computed value will yield us the error we obtained. But this is actually what an error rate or what an error tolerance is, but we need to somehow define it in a more technical and a formal manner. So the way to do so is that we use what is known as infinite norm. So an infinite norm is, what is that? Let's define it. What is an infinite norm? An infinite norm is, well, we can write it in different manners. Say this is the error, right? With tolerance. In other words, our error tolerance, or the amount of error that we can tolerate, or error rate in short. Okay, so the thing is, now the problem, we don't know how many iterations it would continue, right? So I don't know how many iterations it would take, but I can arrange it. So say this is, I will explain what I'm writing. Just let me first write it, and then I will explain what I have just written. So here's k minus 1, and this absolute value should be, well, actually this is the error, and this should be, let's move a little bit right to the right. All right, what is known as error tolerance. So we put an error tolerance to stop the iteration process. So in other words, guys, we don't know how many iterations this process continue, this computational test continue, but in any successive iterations, in any successive 2 iterations actually, you know, k here is the power, which I represent k and k by k and k minus 1, actually just the number of iteration. So k means kth iteration, and k minus 1 means k minus 1, k minus first iteration, and xi is the unknown variable that is in question. So here's the thing, suppose in the last iteration we find some value for one of the unknown variable, and of course we know the previous value of the corresponding unknown variable, and if the difference between those two values, actually we compute this for all the unknown variables. Say if we have 3 unknown variables, we compute for both unknown variables the same absolute difference and select the maximum one. Because if we select the maximum one, and if it is less than the error tolerance that we pre-assumed, then the others should also less than this error tolerance, and then we are done. Because all the values actually have reached to the desired error tolerance, right? They are all below the assumed error tolerance, and it is time to stop our iterations. So then we are done with Jacobi method. That's why we select the maximum one between those. So in any 2 successive iterations, if the maximum of this difference is less than the predefined error tolerance, then we stop our computation and produce our result. Otherwise, unless we reach to the desired error tolerance, we repeat our computational task until convergence is met. So until we converge to some value. And by saying we converge to the solution, I mean when we obtain this error below the defined error tolerance. Alright, and this is the steps, guys, we need to follow. And again, first we rewrite each corresponding unknown variable in each equation, and then start with an initial guess. If we are not given an initial guess, we take all the values equal to 0, and then we already have rewritten each unknown variable, and then by plugging the initial guess, we start iterating the values and finding the new values for the unknown variables. And at the end of each iteration, actually, we compute the error, right, by taking the infinite norm, right? This is the infinite norm that I've just defined here. So if this infinite norm in any successive 2 iterations is less than error tolerance, then we stop and produce the output at that iteration. So what we find at the last iteration, when we gain the error tolerance, then we produce those values as the output, and this is actually our solution, right? This is our approximated solution. And unless this convergence is satisfied, we continue. So we repeat this computational task. Well, of course, if we didn't put an iteration boundary. So what I mean is that suppose we keep iterating and iterating, and we're not able to go below the error tolerance, but we reach to the maximum number of iterations. Suppose we assume that we iterate at most 100 times, and at the 100th iteration we are still not below the error tolerance, then we can stop if you put that condition, if you put that restriction actually. Alright guys, this is actually the steps that we should follow. Let's see these steps in a real example. Okay, suppose this is the system given to us. Alright, 5x1 plus x2 plus x3 is equal to 12, x1 plus 6x2 plus x3 is equal to 17, and x1 plus x2 plus 7x3 is equal to 20. And now solve this system using Jacobi method. Yeah, let's see how this method really works in a real application. Alright, the first thing, well, of course, before everything, I need to check to see whether or not convergence is ensured, right? So, you know, this is the system. And if I want to write it in the matrix form, I check the main diagonal elements, right? So this is the main diagonal element. If I represent the system in a square matrix form, right? I write the coefficient matrix, so just the left-hand side values. And if you notice that 5 is strictly greater than 1 plus 1, so it's satisfied. And 6 is greater than 1 plus 1. And again, 7 is greater than 1 plus 1. So there's no problem. We have a strictly diagonally dominant matrix, so that means, you know, convergence is guaranteed. So I can start using this Jacobi method. And the very first step to take is what? Well, the very first step to take is I need to write, I need to rewrite each equation, right? I need to rewrite each equation in terms of the corresponding unknown variables. So here you see I write x1.